pick up where I left off before. Okay. Can you see my screen now?
Yes.
The altered minerals. Okay.
Yes.
Okay. Did y'all lose it for a while and then it came back?
It was just blocked out, but
Okay.
we could still see it in the background.
Okay. All right. So we're back again, starting over again with a new recording. So there'll be 2 recordings for today. Okay. Now, altered minerals. These are minerals that have been exposed to different environmental pressures, temperatures, or chemical solutions that actually change the minerals into new minerals. Now, later, when we're talking about our rocks, we're going to get the same concept again. And there's a certain type of rock this happens with classically, and that's metamorphic rock. Hang on to this thought, because when we get to metamorphic rock, that's what's happening in metamorphic rock. The changes are happening. Increased pressures, increased temperatures are the present of new chemical solutions that may change the chemical compositions. Now, what was one mineral changes into another one. It may be the same chemical or similar chemical buildup, but the crystal structure may be the only thing that's being changed. Or it could change with different chemical solutions, change the chemical buildup as well. Now, this usually occurs in temperatures above 150 degrees Celsius. Now, I don't know how familiar you are with the Celsius scale, but water boils at 100 degrees Celsius. Okay? Your body temperature is about 60. Well, normal room temperature is 20 degrees Celsius. So when we're talking 150 degrees Celsius, that's not quite as much difference between room temperature and water boiling added to water boiling. Okay, that was an 80 degree difference. This is a 50 degree difference. So it's quite hot, really, really hot. But look at this pressure. Something above 2,000 atmospheres of pressure. Now, right here on the surface of the Earth, we're usually right around 1 atmosphere of pressure. That's why it's called 1 atmosphere. We have the weight of the atmosphere above us. You might say, wait, the atmosphere is made out of gas. How can that have any weight? Certainly it has weight. I'm guessing most of you have probably checked your tire pressure in your car, right? In the tires of your car. And you usually pump them up to, say, 32, 40, maybe even larger pressures, right? Now that's called gauge pressure. That's not counting an atmosphere of pressure. What 1 atmosphere of pressure is, now again, I was giving numbers in PSI, pounds per square inch. Pressure is force per unit area. Pounds is a measure of force, area is a measure of, square inch is a measure of surface. Now, 1 atmosphere of pressure, this atmosphere above us, is weighing down on every square inch of your body. A square inch is about like, if I could get it, these 2 thumb joints put together. That's about 1 square inch. You got about 1 inch this way, and you put 2 of them together, you got 1 inch that way. Okay? That's 1 square inch. Just think how many square inches there are of your body. Okay? It's a lot. Normal atmospheric pressure is close to 15 pounds per every square inch. It's 14.7 psi, pounds per square inch. It's close to 15 pounds for every square inch. Think how many square inches there are of your body, multiply that by 15, that's the weight of the atmosphere on you. Why is that not crushing you? Because you're pushing back with actually more pressure than that. if you've ever gotten a cut, which way does the blood flow? Does it get sucked in or does it flow out? It flows out. It bleeds out. That's because there's more pressure in your body than is outside your body. Okay? So we're already at, and that's just at 1 atmosphere of pressure. Okay? 1 atmosphere of pressure. Close to 15 pounds per square inch. Multiply that by 2,000 atmospheres, and you got a lot of pressure. Now, where does that happen? Way, way, way deep in the Earth's surface. Okay? Now, here's an example of that. Does anyone have a concept of about what 10 meters is? A meter, okay, this room behind me, the wall behind me here, this is about a 10-foot ceiling, okay? That's, now I'm going to go stand against it. Goodness, I'm stiff, okay? All right. Am I in the picture here? Okay. I'm about 2 meters high, and that's about another meter above me, wouldn't you say? So this room is about 3 meters high. On campus, those rooms were about 3 meters high, approximately. So 10 meters would be basically a 3-story building because you have a little bit of space between each floor. So think of a 3-story building. This house is only 2 stories. Think of a 3-story building. That underwater, 10 meters of water, that adds 1 more atmosphere of pressure. So to get 2,000 atmospheres of pressure, you would have to go 200 more feet, 4 meters of water down. 200 meters? Okay, that's like more than 2 football fields down to get anywhere close to this kind of pressure. That's a lot of pressure. Okay, now here they say examples of this. Garnet is an altered minerals from something else. Does anyone remember what garnet is? That the red stone? Garnet? Or is that yellow? I don't remember. Epidote? Epidote? I don't even know what that is. Talc? I wouldn't have thought it would be altered because it's really soft. Graphite? Yeah, we talked about that. That's real. Serpentine? That's an asbestos source. These are examples of altered minerals that were something else at one time, and they have become altered because of either pressures, temperature, or chemical solutions. Okay. Now, again, this comes into play more under the rocks portion, so hang on to it. Now, one last thing they talk about here are your, and this again I can't find specifically here, your ore minerals. These, remember, on the non-silicates were what they call the element minerals. These are mineral deposits, usually with economic value. Often found in veins, just little strips, and could be sort of thick, but usually found between layers of other rock. Okay? Thin, flat bodies of mineral material. And when they find a vein of them, they sort of try to mine that vein. Okay? Now this is left over from crystallizing magma, or it was been flushed away by hot water solutions. One or the other.
Dr. Fowler.
Yes.
It's time to take roll again.
Oh, is it? Thanks for, oh yeah, you're right. 2 minutes over. So let me take it, and I'm going to try to do this using this board here.
Yes, sir.
All right. All right. I see Bridget is still, my internet connection is unstable. I don't know why. It seems like everything's going wrong today. Okay, Bridget's still here. Let me get her marked.
It's because the weather is bad out there.
Is it? It seems pretty nice here. Have y'all got storms where you are?
It's looking dark and cloudy like it's about to.
Oh, really? Okay, I think I do see a few more clouds than I saw earlier today. So Bridget's here, Scott's here.
Yep, here.
Okay, let me see if I can find Scott. There's Scott.
Yes,
Okay.
sir.
I see Caitlin's still here. And
Here.
obviously been able to hang in the class for a while now. Good. Capri is still here. She had trouble, it seemed like, getting in. Well, I'm glad you're here. Cormisha is still here. She was here from the very beginning, I think. Yep. There's Cormisha. Roy. Roy showed up at the top there. Okay. Because the names move around here. I've got Bridget, Caton, Capri, Cormisha. David is still here. Let me get David. Where are you hiding, David? There you are. Okay. All right. Let me bring it on down. Harry's still here. Game of Thrones guy. Okay. Jacob's still here. Got him. Okay. Nikiah is still here. I almost said it wrong. There you are. Okay. Roy's still here. Scott's still here. Is Valerie still here? Yeah, I guess she is. Okay.
I'm still here.
I know, you're the one that told me. Okay. And I think you're the last. Okay. That should be 11 students and me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It looks like we may have lost Thomas. So if you see Thomas come back in, I'll get him for lab period 2. Now, it doesn't look like we're going to have a lab today, but we'll try to finish the chapter or at least make good progress on it, and then we'll get back. And so I can almost guarantee you we'll have the lab next time. All right, so let me close this out so we can get back to where we were. Okay. So ore minerals, often found in vein, thin, flat bodies of mineral material, usually left over from either crystallizing magma that came out at a certain temperature or pressure or whatever, or things that were flushed away and brought back in hot water solutions. Here are some examples, and I don't know why they give these specific ones. Pyrite, which is iron sulfide, that's called fool's gold, I mentioned that one. And chalcopyrite, which is the sulfide of both copper and iron. Remember your carbonate, we had either calcium carbonate, calcite, or we had calcium and magnesium carbonate, which was dolomite. And you know, there's a town in Jefferson County or one of the close by counties named Dolomite. I bet you they had lots of calcium magnesium carbonate there. That must be why they got its name. Well, so with a copper and iron sulfide, that would be chalcopyrite. Now, these are not huge economic values. They're just examples of what you would call ore minerals found in veins. Okay. Now I can't get it to advance, so let me click on the slide again. Here we go. All right. Now, we're finally finished the mineral half of the chapter. I'll say half, it's not exactly half. Okay, probably a little more. Let's move now to rocks. What are rocks? Okay, you all have a pretty good idea of what they are. They're aggregations, that means combinations, grouping together of one or more minerals. Remember I said minerals were the building blocks of rocks. You could have one or more than one mineral in a rock. But also rocks allow some other materials that may not be minerals. Okay? Minerals are physically combined to make rocks. Now when they say physically combined, that doesn't mean chemically combined. There could be some chemical features to it, but it's mostly a physical combination. For instance, they are glued together, okay? And this is some of the perhaps other materials. Maybe there's something they call a cementing agent that is not really a mineral itself, but it's holding the various minerals together. You can think of what concrete is. Concrete is a mix of cement, which is your cementing agent, with something that it's cementing together. Usually sand grains, but it could even be gravel, okay? Different types of concrete could be made up of sand, or it could be made up of gravel or something else, but you have something holding it together. That's your cement or your cementing agent. Well, rocks are a variety of minerals and maybe other things too, being held together by some sort of agent, which are sometimes called cementing agents. They're physically combined, not chemically, so they're changed in any way. They're minerals put together. Most rocks, again, just like we saw, are silicate minerals. Now, limestone, like we said, has a lot of calcium carbonate, which is calcite, and dolomite, which is calcium aluminum carbonate. But guess what? Even limestone has silicate materials in it. Your non-silicate minerals don't, but the rocks where we get them from, they may have them in there. Okay? So here's the classification scheme. Rocks are classified based on how they were formed. 3 main groups, and this is what most of the rest of the chapter is going to be about, talking about these 3 main groups. The first of these is igneous rock. Now, what word do you almost see in igneous? The I-G-N. What if that E was an I?
Igneous.
Is what? Say again?
Igneous.
A little louder.
Igneous?
Yeah.
Igneous?
What does that mean? It almost looks like the word ignite, doesn't it? It starts the same 3 letters, right? They came from fire. Okay? Other words, they came from molten material. That's what an igneous rock is. Sedimentary rock. What you reckon that would be? Something that is settled out. That's a sedimentary rock. Metamorphic rock. Now, I don't know if any of you are used to the term metamorphic. Any of you? Perhaps in biology, you studied something that metamorphosized. The classic example is the caterpillar metamorphically becoming a butterfly, meaning it's changed its structure big time, okay? Meta usually means big. Morph means the structural of it. Changed its structure. Well, that's what a metamorphic rock is. Remember when we're talking about altered minerals, pressures, temperature, and stuff like that? That's what metamorphic rock comes from. So we're going to hit these individually. So let's start with igneous rock. As I said, rock that formed from magma, either above the Earth's surface. If magma is above the Earth's surface, what do we call it? Think of volcano. Lava, exactly. Or below the Earth's surface, and then it's just called magma. Okay? If it formed from magma, it's an igneous rock. All rocks were at one time igneous rock. Later, when we talk about sedimentary rocks come from pieces of other rock that broke off, shared, dissolved, did whatever, but later settled out again and formed sedimentary rock. They were at one time, sometime in their past, igneous rock. Why do we know that? Because the Earth was formed from molten material that came out of the explosions of the sun. We were at one time totally magma, okay, or lava. We were all igneous rock, okay? It may have been billions of years ago it was igneous rock, but all rocks were at one time igneous rock. Now, This is what we were talking about with time before. The cooling rate determines the texture. Texture is how rough or smooth or the degree of roughness that a rock has. Okay? So if a rock was cooled very quickly in its formation process, it tends to have very small crystals, so it's a fine texture. If it cooled very slowly, it tended to form big crystals, and that gives a very coarse texture. So let's look at what factors into those cooling rates. Here it is. Intrusive igneous rock. Now, focus on the prefix IN. Intrusive igneous rock formed inside the earth, beneath the earth's surface. Intrusive igneous rock. That generally means if it was inside, it cooled more slowly. If it cooled more slowly, it gave you larger crystals. If it had larger crystal, we call it coarser grained or coarse textured rock. That's intrusive igneous rock, cooling slowly, form larger grains. Extrusive, think exit. It exited the Earth's surface, okay? So therefore it formed from lava, was magma, but became lava when it reached the surface, formed from that, so therefore it cooled really rapidly. And if it cooled rapidly, it gave you small crystals, meaning fine grain, not coarse grain, fine grain. Okay? Now, here's the example. Here is a piece of granite. This is a coarse grain. What that means, intrusive igneous rock. We don't know this right now, but I'll tell you, granite is igneous. Okay? Intrusive igneous rock formed beneath the surface of the earth that formed a slow cooling process, forming large crystals, coarse grain. You can see the roughness of this. Now, sure, you can polish it and make it smooth, but even then, you can look at it and see, if I could get my cursor to come back, there's a crystal there. You can basically pick out the crystals, okay? Dark crystals and light crystals and things like this. They're different minerals making up this rock, but they're usually large crystal size. Now, here's a piece of hairy obsidian, which is exactly the same chemical structure as granite. Exactly the same. But the trouble is, it formed on the surface or above the surface of the earth, rapidly cooling, so rapid that it didn't even form crystal structures, and this gave it the glassiness. Okay? It's called a volcanic glass. Okay? The curved surface is common to non-crystalline surfaces such as glass. So obsidian is not a mineral because it doesn't have the crystal structure. It is a rock because it's made out of the same material as it, but it's a solid, but it's obsidian. So it seems sort of, well, I guess it makes sense. Anyway, they claim this is what you make the swords from, that you can kill the whites or whatever it is they kill in Game of Thrones. Okay. Any questions on this slide? Now we're talking about rocks, not minerals. Rocks are made up of different minerals. What you see in granite here, you see little dark specks. That's probably high iron content rock. You see brownish color. That's probably your plagioclases and your feldspars. You see the whitish material. That probably is quartzy type material. Okay? So you know there's different minerals in that one piece of granite. So, how do we classify the igneous rock? All rocks are classified igneous, sedimentary, or metamorphic, but within igneous rock, how do we classify that? Well, two factors come into play. We've just talked about both of them. Mineral composition, what types of minerals make up those rocks? Secondly, what's the texture of the rock? In other words, is it coarse textured, meaning large crystal sizes, meaning it cooled slowly? Or is it fine texture, meaning small crystal sizes, meaning it cooled rapidly? Okay, so there's one. Let's look first at the mineral composition. Well, is it high iron content, non-ferrous composition? Now, they're talking about a figure. Let me show you the figure. Here's the figure. Over here, and they did it on purpose, the light-colored side of this slide is the low iron content. The darker means more iron. The lighter means less iron, more silica. Remember? Down here, lower silica. Up here, higher silica. Here, lighter. You start increasing calcium. Remember, your calcium feldspars came out of solution first, and then the other feldspars later. Iron, I wish they wouldn't put O's here. That's common to do, but your iron and magnesiums came out last. Okay, high content of silica is to the left, high content of iron to the right. Those are the majors. Okay, so the non-ferrous composition on the left of the figure, low density, meaning not much weight per unit per unit volume. Light in color, meaning not much iron content, which also contributes to density. And the granite is the most common example. Most granite is light colored. Okay? Now, when we're having our master bath, it's not a very large master bath. This is a 1930s house. They didn't put large bathrooms in them. But when we had it redone, the guy that was doing the floor said, "Oh, I want some colors. Why don't you go get me..." Okay, my internet connection is unstable. I'm going to quit talking. Okay. Was I getting a little garbled then?
No, you completely went out for a moment because I thought it was mine.
Okay, that's what happened. My internet connection went down for a bit. So I quit talking about this material. I just started talking in general. Okay. Well, he asked us, he said, "Go get me some black granite." Now, that's before I ever taught this series of courses. And I just went to the Home Depot or someplace, wherever I went, and said, "Do you have black granite?" He said, "Oh, yeah, here's some." And he gave it to me. And it was a dark mineral rock. Well, I later told my niece that, who had studied geography and geology on her master's, and she said, "There's no such thing as black granite." I said, "What?" She said, "No, there's no such thing as black granite." So I didn't argue with her. I figured she knew what she was talking about. Like in the next year, I started teaching this course, and I found out she was absolutely right. There is no such thing as black granite, even though the people who use it call it that. What they were talking about was basalt. Basalt is a rock, similar like granite is a rock, but it's not, its high content of iron is very dark, and granite is light colored. So what I got was sheets of basalt, not sheets of black granite. There is no such thing. Granite is by definition light colored. Now, we have some examples of it. Unfortunately, we won't be on campus to see it. That is some pretty dark looking granite, but they're more tend to be more of the dark browns. Not so much. There is some biotite in granite. Remember those little flecks of darkness? That was biotite, probably. The brown places were the plagioclases, okay? And the potassium feldspars or orthoclase, they're lighter yet, but they still have some color to them. So the darker granites are more biotite and more plagioclase, fewer feldspars, and certainly less quartz. Okay, so you can have some darker granite than others, but there's no such thing as black granite. Okay, so granite is a common example. Now, granite though is coarse grained, meaning it did form beneath the Earth's surface. It's intrusive igneous rock. okay? But it's also low iron content, low density, light colored. Now there's another mineral called rhyolite, which is just like granite or very similar to granite, only it's very fine grained. When you have a piece of that, you'll not see but very, very small crystals, like salt crystals or something about that size, because they won't be that color. Granite, you'll see larger crystals. Okay. Your ferromagnetic composition is on the right. This is again your mineral composition. Non-ferrous composition doesn't mean it has no iron, it just has less iron. Your more ferromagnetic composition is on the right here, and that's your olivines. Olivines is almost totally iron-based silicates, ferromagnesium silicates. Then you get to your basalts, which they mention here. Basalt is a fine-grained, dark ferromagnesium compound. It has some calcium-rich plagioclase in them, but remember the calcium is over on this end too. Calcium-rich plagioclase, but it's mostly darker. Basalt is fine-grained. Now the house that we built over on the farm, a 2-bedroom bungalow over there where we were last weekend, its countertop is very dark, but it's large crystal size. So when I saw that, I said, this must be gabbro. And then later when that same niece came to visit, she said, oh, nice piece of gabbro. Oh, yes, I knew that. Okay. Well, I thought it was true anyway. I'm not as familiar with these in the middle, diorite and andesite. They're kind of in between. They're fairly dark, but they get more brownish and less and more grayish rather than blackish, but you don't have the light colored quartz and potassium feldspars. So on the right hand side, your darker colors, higher density, mostly because of the iron content on both of those reasons, and one of your common examples is basalt. If we were to be on campus, which we can't, and we won't this term, I brought pieces in from broken pieces when they were putting the thing in, and I'll let you see, would have let you see what basalt looks like, because it's my guess that's what basalt was. Very fine grained, very dark colored. Okay. Whereas granite, there are pieces of granite in there too in my collection, but we're not there to see it. All right, that covered our igneous rock. Okay, we have gone to through page 447. Now let's jump back a little bit to 446 or 1711 if you're following in your smaller books. Science and Society, the cost of mining mineral resources. And there's a lot here. There are questions to discuss. If this prompts you or promotes you to think about things like this and you're interested in it, you can possibly find some potential paper topics here. Okay? But it's still well worth a read, even if you've already decided on a paper topic. Then at the bottom of that page, which we saw similar to in the slide set, is a piece of obsidian, which doesn't look at all like granite, but has basically the same chemical composition. It's just real slick looking because it's glass. And then there's a couple of examples here. Igneous rock classification based on proportion of minerals. The 17.3 is pretty interesting to look at because you can use the table that we're just seeing here and trying to piece together. So let's do one of these. Okay? Says igneous rock classification is based. Let me move this in front of me.
I'm sorry, we can't hear
I know,
you.
I'm moving it in front of me. Igneous rock classification is based on the proportion of minerals present in the rock shown in the. Goodness gracious. For a given igneous rock name, this proportion varies based on its. Wow. Based on figure 1713, that's the one we see right here on the slide. What is the range of percentages of each mineral in granite. Okay, so let's look at that. Starting from the bottom, granite over here ranges from close to 0% quartz. You might say it's 1 or 2% quartz, up to, I'm guessing that's about 30% quartz. So from 0% or maybe 5% quartz to 30% quartz. If you go down at the bottom, you'll see 0 to 32%. My guess was pretty good. Okay, granite would be what percentage potassium feldspar, orthoclase. Again, it looks like it's starting at close to 0% here and going up to here. Well, if this was, say, 32%, this looks like that's probably close to 90%. Well, 30 to 2 from 90 would be something like 58%. Well, they say 53%. Okay? So 0 to 53% feldspar, potassium feldspar, orthoclase. How about sodium-rich plagioclase? Well, that varies from, I can't get my, oh yeah, in granite, this looks like maybe about 70% up to maybe 95%. So I would say that would be from, and the 70% here is from the bottom, the 95% is from, say, 90% here, so that's 5% sodium-rich plagioclase down to, what do we say, 70%. So let's see what they say. Sodium-rich plagioclase, they say from 10% to 70%. So this, I guess, starts a little above 0. Okay? And then biotite looks like it ranges from, and this is approximate, 30% biotite for the darkest granite, and for the lightest color granite, maybe 5%. So they say the biotite is from 5% to about 30%. Okay, so biotite 5% to 30%, sodium-rich plagioclase 10 to 70, potassium feldspar 0 to 53, and quartz. So it's sort of interesting to use this table to estimate. Okay, so this granite down here at this end is going to be some pretty dark granite. No quartz in it, no potassium feldspar, just some browns and blacks. Okay, and that piece that we have on campus that's really dark, I can't remember what its name is. It seems like it's from Brazil or somewhere. That would almost certainly be at that end of the granite range. Okay. So I'm not going to do the others. That was just, to me, fairly interesting to look at. So let's move to sedimentary rocks. Now this starts on page 447, which is your page 1712 if you got a smaller book. And what sedimentary rocks are rocks that are formed from particles or dissolved material. So keep that in mind. Either little particles of material or dissolved materials. One or the other, sometimes a mix of both, from previously existing rocks. Where do the particles come from? In a later chapter, we're going to talk about weathering. Weathering breaks down other materials. If it's broken down by mechanical weathering, that usually breaks it into small pieces. These are the particles. If it came from dissolved materials, that would be chemical weathering. That still is coming from previously existing rock. Okay? All right. Now, sediments. Now, this is an accumulation. What do we mean by sediments? Accumulation of either silt, sand, or other materials that settled out of water. Most of the time, these sedimentary rocks fell out of water. Okay? Now, what do we mean by silt? Well, I've already described to you what clay particles are. Remember that dime we sliced into 1,000 equal pieces, and anything less than 2 of those slices, tiny little slices, and on down, that would be a clay particle. A silt particle would start there and build its way up to about the thickness of a dime, maybe smaller than that, okay? A sand particle goes to about the size of 2 dimes put together. That would be a sand, okay? You could have other materials. Gravel is bigger than sand, okay? Now, sometimes we talk about sand as that white stuff that you see at the beach. That's mostly quartz. Sand doesn't have to be quartz. It's just anything in that particle size. So those are your sediments. Accumulations of either clays, they don't mention clays, silts, sands, or any other material that settled out of water. Gravel, boulders, whatever. Okay. Now, 2 types of sediments. One of these is called clastic sediments. These are accumulated from rocks at various stages of being broken down physically, mechanically. Okay? Little chunks, pieces of rock. That could be small pieces like silt, bigger pieces like sand, bigger pieces like gravel, bigger pieces like boulders, okay? Anything that broke off a bigger rock, okay? Clastic sediments are pieces of rock material, generally that broke off mechanically, okay? Now, this table you're going to see over and over again. It seems like at least 3 times they show you this table. Right now, we're only talking of the top half of this table. Clastic sediment types. Now, if that clastic sediment was very small, silt. Okay, let me give you a sort of a layman's view of what the difference in sand and silt. If you have sand and rub it between your fingers, it feels gritty. You can feel those little particles moving between your fingers. If you did the same thing with silt, that would feel like flour between your fingers. Really slick and smooth. You can't actually feel individual particles. That would be a silt. A clay is so incredibly small you would never see it. It would actually go into your pores. Okay, it's incredibly, incredibly small. So anything that would be a floury texture, that would be a silt. Anything that's a gritty texture, that would be a sand. Now, of course, you know what gravel is, chunks, okay, and boulders are big chunks. Okay, so anything that's made out of the silt, that floury type material, or clays, the rock that would be sedimented out with them would be either called siltstone, claystone, and another name is shale. Okay? Now, shale doesn't have silt or clay in the name, but it is made out of those very small particle sizes. Okay? These are rocks that are made out of sediments from those sizes. Now, I think there may be one other, and they don't mention it here, but I see it advertised, and everything I can read and understand about it, and I think I've actually felt it before, something called soapstone. It's so slick, it almost feels like it's a bar of soap, okay? You don't feel any gravel in that at all, any grittiness at all. So that to me has to be another type of a clastic sediments made out of silt or clay, okay? Now, if it's made out of sand, then it's called sandstone. Now, I don't know if any of you have ever been up around where I've seen a lot of it, Winston County. My wife's family had a place up there on Smith Lake, and most of the rock I've ever seen around there that was naturally occurring is sandstone, okay? It is definitely, when you rub your hand over it, you can feel the grit. But it's a sedimentary rock, a clastic sedimentary rock, and those are mostly sandstone. Some of the examples I had when we were on campus, you would see, and I got them from Winston County, at least some of them from there. Okay, but what if you had clastic sediments that were even larger than sand? And mostly we're talking here about gravel. They have two names, conglomerate or breccia. And I don't know if that's pronounced breccia or breccia. I've never heard anyone pronounce it to know what was correct. These have a difference, and it's going to show up on a later slide. In fact, let me go ahead and show it to you now. Here it is. Conglomerate has rounded fragments. Now these are gravel-sized fragments. Breccia or breccia has angular fragments. So I'll show you a picture of some breccia coming up. I don't think I have a picture of conglomerate. Okay, conglomerate, the gravel is rounded, which basically to me means it's been undergone a lot of weathering by water, running through water, and it knocked off the angles. Breccia or breccia would have very sharp angles in the fragments. Okay, so all right, so those are the three further breakdowns. Okay, sedimentary rocks broken down two ways. Classic sedimentary, meaning pieces of rock, particles of rock. We haven't gotten to the chemical. We'll get to that in a minute. The clastic sediments broken down basically into three pieces, three parts. Silt or clay, very slick type, and that's siltstone, claystone, or shale. You can't feel any grittiness when you rub across those. Sandstone feels like sandpaper when you rub across it. Okay, you can definitely feel little particles of sand. Breccia, conglomerate or breccia, you usually can look at that and see these big old chunks that's bigger than sand, but they're cemented together with some type of material. If they're rounded, those are conglomerate. If they're angular, it's breccia or breccia, however you pronounce it. All right. Now, let's break down our particle sizes even more. Now, they say clay is dust. Well, a clay particle is even finer than dust, okay? It is submicroscopic in size, okay? Silt particles, yeah, that would be dust. Think flour, dust, that kind of thing. Sand particle, and by the way, here are the things we're talking about. Most of what I've heard called in soil science, they say less than 2 microns. Now, a micron is a thousandth of a millimeter, okay? It's a millionth of a meter. And I'm just going to see how this breaks down compared to that. Let me get my thing here. 1 divided by 256. That's about almost 4 microns. Okay, so they'll say something less than 1/256 millimeters. That would be basically, they're saying less than 4 microns. The soil science definition is less than 2 microns. So theirs is almost twice what I call, but it's still so incredibly small. That would be 4 of those tiny little slices of a dime. If you sliced a dime into 1,000 equal slices, 4 of those put together would be the biggest clay particle, dimension of a clay particle, which is still incredibly tiny. Silt would be between that and 1/16 of a millimeter, which is still very fine. That would be flour or dust. Sand between that size, 1/16 of a millimeter, up to 2 millimeters. 2 millimeters would be the thickness of 2 dimes together. So that would be the largest sand particle. Anything larger than that is called gravel, and that's up to 256 millimeters, which is about 10 inches. Yeah, there it is, 10 inches, there it is. That would be what we call gravel. Anything larger than 10 inches that would be called a boulder. Now, it's a pretty small boulder in my mind, but that's how they classify it. All right. Now, on to the next slide. Chemical sediments. This is the second kind. You have classic sediments, which are chunks, particles of formerly existing rock. Chemical sediments means that rock that was there was actually dissolved. Now, what would have dissolved the rock? Water may dissolve the rock, or add a little acid to the water, and that could dissolve the rock. Maybe make some very, very hot water, and that may dissolve the rock, or even very, very hot acid water would really dissolve the rock, or possibly even, I don't know, I don't think magma, that you wouldn't go that far. Anything that would, any chemical, including water, that would dissolve the rock. Take it out of being a rock and into solution. Okay? Now, there's 3 sedimentary pathways. And like I said, chemicals are involved. Chemical precipitation from solution. Now, does that make sense to you, chemical precipitation? When you think precipitation, what do you think? Do you think rain? That's what I usually think. Okay? That's not necessarily precipitation. Chemical precipitation, let me describe to you one of my, in fact, I think it was my first chemistry lab in college. They gave us a clear liquid, and they told us what was in it. It was silver nitrate. Okay? It was a clear solution, silver nitrate. They gave us another clear solution, and that was, let me see if I can remember what it was. I think it was sodium chloride, just salt water. Okay? Silver nitrate and sodium chloride. Both of them clear solutions. Didn't see a thing in it. But when you drop both of them together into a thing of water, suddenly you had white particles falling out. What it was, to be a chemical solution, clear chemical solution, that means all the silver ions and all the nitrate ions had been separated from each other by the water or acid or whatever it was that kept them separated. Okay, I think it was just probably water. Okay, water is a great dissolver, okay, and it kept them apart from each other. They were floating around as ions in solution. Same thing with sodium chloride. You put salt in water, as long as you don't put too much in there, it will dissolve. And you don't see the salt particles anymore because the sodium ions separate from the the chloride ions, and they're floating around in solution. But then when you mix the silver nitrate with silver and nitrate ions and the sodium and chloride ions together in the same container, all of a sudden, any time that silver ran into a chloride, it came out because it precipitated out, meaning it fell out of solution. If you ever did any rock climbing or glacier walking, the precipice is the thing you could fall into, okay? Something to fall out, that is precipitation. Rain falling out of the sky is precipitation. Hail falling out of the sky, snow falling out of the sky, that's all precipitation. Something falling out, a chemical coming out. So let's say that we had a solution coming down from a river somewhere that had come off the land somewhere and had all these chemicals in solution. And they met at the bottom of the ocean with another group of chemicals from another river somewhere, and they met down where it was getting really cold down there, and now some things come out of solution. That's chemical precipitation. That's a type of sedimentary rock that would come out of there. Now, that's one, chemical precipitation from solution. That's one sedimentary path. Another one, remember our example of the salt and water, evaporate the water away either by boiling or just letting it evaporate naturally, and sure enough, you get crystallization. That's a sedimentary process. You had the chemicals in solution, but now the water evaporates away, and now the chemicals come together, forming a crystal. That's a chemical sedimentary rock, just like the other was a chemical sedimentary rock. Now one other, and this is a little shaky in my part, is biological sediments. Now, remember, biological things would not be classified as minerals, but these biological sediments could be classified as rocks. Because remember back when we defined what a rock was, I'm going to fly back there quickly. Aggregation of one or more minerals and perhaps other materials. Biological sediments would be other materials, not necessarily minerals. So, biological sediments could fall into there. And you'll see an illustration of it coming up fairly soon. Okay? Here's that same table again that we talked about before. Now we're looking at the bottom half of this table, the chemical sediment type. Okay, one chemical sediment is calcite. Okay, calcite is calcium carbonate, but that comes out of solution forming these crystals. Now, if we were in the lab, a student many years ago brought me some calcite crystals. Where did he bring them from? He was a young guy, probably within your age range, but he was also a coal miner, okay? And he mined coal, and I don't know why this is true, but chemically it happens, the same places that coal comes out, right next to coal, you get calcite crystals, okay? Coal is mostly carbon. Calcite is calcium carbonate. So guess what? They're sort of related, but they don't look at all like each other. The calcite crystals are clear as glass. Beautiful, sharp little crystals. The coal is dark as night, okay? And they're right next to each other. And there's an integrate in between the two, which I'm sure is a mix of two. Calcite crystals are a chemical action, I'm guessing chemical precipitation from solution. The rock that calcite shows up in is limestone. Okay? Limestone's the rock, it's not the mineral. Now they talked about it before as, well no, I guess I was talking about it. Calcite's the mineral, limestone's the rock. Okay? Another chemical is dolomite. And that was calcium and magnesium carbonate, and the rock is dolomitic limestone. Its technical name is dolomite, but it's really often called dolomitic limestone. Now, being from Alabama, and the fact that Alabama is a state that's underlain mostly with limestone, not with granite. Granite's an acid igneous rock, okay, which doesn't have a lot of natural fertility to it. It has some, but not a lot. Whereas limestone, yeah, it makes great soils, okay? I'm a soil scientist, that's what that turns me on, okay? Now, if you have acid igneous rock, sometimes the acid igneous rock gets too acidic and it's hard to grow your crops on it. So what you do, you lime the crops with limestone, very finely ground limestone. Grind it down mechanically until it's more like a powder. It will have a little grittiness to it, so it's sort of between sandstone and, silt size and sand size, okay? That would be what they grind it down to. That's not naturally occurring, that's been processed by man. If you ever do need to lime to change the pH of your garden, your field, your yard, whatever you need, if you can, go with dolomitic limestone. Here's why. Calcium limestone, what they call limestone, is mostly calcite. And as I said before, even though plants use calcium, it's everywhere. You really don't have to add calcium, it's everywhere. But plants do definitely need magnesium. And here's why. Remember when we were talking about the iron in your blood being carried around by that hemoglobin molecule, which is like a claw with iron in the middle of it? And that iron can either be reduced iron, which gives you the blue blood, the venal blood, or bright red blood, which comes from highly oxidized iron that has more oxygen, that's in your arteries, and that's the red blood. Ferric oxide as opposed to ferrous oxide. We talked about that last time, or sometime. Okay? Well, in a plant, in a claw almost identical with hemoglobin, is a claw that's in every leaf, green leaf you see, and that claw is called chlorophyll. And what is in the middle of that claw, rather than iron, is magnesium. Okay? So plants have to have magnesium. So why not, if you're having to lime your soil, give them some magnesium. Use dolomitic limestone. Now here's 2 reasons you may not. Number 1, calcitic limestone is way easier to come by. Every place that sells lime or limestone, that's usually what you're getting. But if you request dolomitic limestone, it's probably going to be a little more expensive. There's 2 reasons. Well, number 1, it's you have more calcitic limestone out there than you have dolomitic. But the other reason, dolomitic limestone is harder. Somehow that magnesium makes it a little bit harder because magnesium hangs on a little bit tighter. And because it's harder to grind down to as fine as dust. And people say, no, use calcitic, it's faster acting. Sure it is, because it's smaller particle size. But dolomitic limestone, it may take longer for it to dissolve, but when it does, you also are giving your plants some magnesium that they need. Okay. So dolomite or dolomitic limestone, that's the rock. Another chemical sedimentary rock was naturally occurring gypsum. We talked about that. That's calcium sulfate. Now the rock that it comes from is also called gypsum. So the particle, the composition, the mineral is gypsum, but then they also call the rock gypsum. And it's hard to tell which they're talking about. If it has other materials in it, it's probably the rock gypsum. If it's pure, fairly pure, that's the mineral. If you can see those crystals very clearly. Okay. Another chemical sedimentary rock would be the mineral would be halite, which is simply sodium chloride. That's one of those halogens, okay, that we were talking about, sodium chloride. And the rock is basically what they call rock salt, okay, that you used to use when you were doing ice cream. We talked about that last time too. Okay, or in one class we did anyway. Now, here, remember back here when it said biological sediments that may be a part of a rock? Here's an example of this. This is a piece of limestone. Now, you can't see probably the individual minerals in there, but I'm guessing that might be a little calcite crystal. That may be one. It's all hard to tell. But there's probably mostly calcium carbonate in here. I wouldn't be at all surprised if there's a little bit of quartzy material in there too, because it's an accumulation, an aggregation of several types of minerals and other materials. Here's another material right here. What does that look like to you? A seashell. Biological sediment. That's what they were meaning back here. You can have biological sediments in a rock. There was an area in Burke County, Georgia, where I grew up, okay, called Shell Bluff. And Shell Bluff is loaded with pieces. I'm sure it must be limestone like this. At one time, the Atlantic Ocean, that was the beach, and that's where the shells formed. But later, the oceans receded as the glaciers probably, well, whatever happened. That several things could have been happening, but there is limestone with actually biological sediment in it. Okay, piece of limestone, a sedimentary rock, chemical sedimentary rock, formed underwater, sometimes with the remains of living organisms. That wouldn't be a mineral, that shell, but it would be part of a rock. And it says, can you see the mold of a brachiopod fossil? There it is, the shell. Okay, here's another piece of rock. This is sandstone. Now these layers were at one time fairly close to being horizontal because they deposited out of water. Okay, this is clastic sediments. That's chemical sediment. Limestone is chemical sediment. This is clastic sediment. Sandstone. You can see the layers of different color sand. Okay, they deposited at different times. Now, in a later chapter, we're going to talk about something went on here that bent those layers up. That's a different chapter. Don't worry about that now. This happened to be one from Tasmania, Australia. Wow. And by the way, the different colors here indicate different amounts of iron. Okay? They're iron oxide. That's what they're saying. I couldn't read the word. Iron oxide banding in there. The darker colors is more iron oxide. Okay, or the redder colors anyway. This is one of those pieces of breccia. This is way bigger than sand. These are gravel pieces. Okay, but look at the angles. Because they're angular, this would be breccia. Now, if all the pieces were rounded like this, this would be conglomerate. But you see, even this piece has an angle to it. So if it's predominantly rounded material, it's called conglomerate. Now this piece up here looks, if I can get this back, goodness, it shows up. Okay, that looks like it's more rounded. So if it was all made of those rounded materials, it would be called conglomerate. But this one is sort of angular. Most of those are angular. So therefore, this would be breccia. This is a piece of breccia. Again, a clastic, meaning actually particles. You can see the particles that form from consolidation of large angular fragments of solid rock. Now, there's different kinds of rock in here. Okay? This is light-colored rock. That could be quartzy rock. This could be plagioclase. This could be, there's different rocks here. It doesn't matter. Sandstone doesn't, sedimentary rocks don't care where they came from. They're just sediments of various sizes of rock. Okay? That fragment came from Colorado. Okay. Now, here we see that figure again. This shows all of it together. Clastic sedimentary rock, larger than sand, breccia down here. Could be conglomerate if it was rounded, but these are angular, so that's breccia. Clastic sedimentary rock, sandstone. The particles are sand size. You can almost see the grittiness there, but it's not big particles like this, it's small particles, sand size particle. Less than 2 dimes in thickness, okay? They don't show any siltstone or claystone. You wouldn't tell much about it because it's very slick, okay? Or chemical sediments, this one here, limestone. Mostly calcium, calcite is the mineral mostly in there that makes it limestone. I bet you got some quartz in there that always shows up somewhere. So it's not strictly made out of calcite, okay? But it can also have biological pieces in it as well. Other materials. It doesn't have to be all mineral. Okay, but that made from in the ocean somewhere the combination of calcium carbonate and other materials that happen to be down there, which predominantly calcium carbonate, that would be limestone. All right, now how do these sediments actually become rock? Because that sediment is just pieces of rock or chemical combinations of rock. Well, lithification, when you see the prefix litho, think rock. And this is lithification, rock forming process. Two main parts. First, after you have the sedimentation, it's not rock. It's just layers of sediments, okay? But the first thing that makes it into a rock is when you compact it. You get layer over layer over layer over layer over layer. These upper layers are not rock, but somewhere down there, these are getting compressed and contracted more and more, and they start the process of becoming rock. What happens is, as more and more layers get on top, it gets heavier and heavier. You start reducing the thickness of that deposit because you're pushing the particles closer and closer together. Also, remember, water is what sedimented this out in the first place. There's usually water in between those layers, okay? Now it gets squeezed out because the pieces of rock are formed closer and closer together, okay? But that water, by the way, was not probably pure water, because water dissolves all sorts of stuff in it. And part of the stuff that's in the water are these cementitious materials. So the spaces between those sediment particles that the water was squeezed out, now they're being filled in with this chemical deposit that forms a cementation function. The chemical deposit binds the particles together, okay? Just like if any of you have ever mixed concrete, you put the cement in, you put your sand or your gravel or whatever your particles in there, and then you add water and you mix it together. You don't want to get it too wet. If it gets too wet, it's weaker concrete. You want the minimum amount of water, but it's harder to mix because it doesn't have enough water to really soup up the way you want to, but you just keep mixing and mixing, and then when you get it there together, sometimes they vibrate it, sometimes they just pound on it, anything to do to squeeze out the water and get those cementing agent, that cement, to bind those particles together. So that's the second part. Number one is compaction, which squeezes the water out, but the water leaves behind the dissolved materials that were dissolved, leave some of those behind, they become your cementing agents, and the spaces between the sediment particles are filled with that chemical deposit. Now, I mentioned our master bathroom. I wish I had a piece of it here I could show you. The reason the guy who laid the tile, he was just an artist. He was so good at what he did. He thought it would just be too boring to have these white pieces of stuff. Well, what it was, we found, I think at Home Depot or Lowe's or somewhere, fairly cheap. It was made out of pieces of marble. It's not marble, but it's made out of waste pieces of marble. Wherever they made marble slabs and marble countertops and marble other things, they had little pieces, broken chunks and stuff like this, sedimentary pieces of marble left over. And then they mix this, whoever bought up all that or just gathered together all that material that would have been waste material, mixed it with a cementing agent, probably in solution with water, and then pressurize it, compacts it, squeezing it out, and then letting that cementation occur, and then they sawed it into slices, polished it up, and it made a really pretty floor. It looks sort of like marble, but it's obviously not marble, It's not nearly as expensive as marble was, but it contains parts. That's really described what this compaction and cementation process is. Here's a graphic illustration of it. The sediments land, and they land in any sorts of form and stuff. Usually water is still mixed up among them, and then more layers go on top of it, and this is what they call the overburden. That's the stuff on top of it. It pushes these particles closer and closer together in the same process, squeezing out the water. That's the compaction part. And then when the water leaves, it leaves behind little bits of dissolved material in them. That then, as the water dries up or disperses, that becomes your cementing agent, which holds these pieces in place. Let's go back to that breccia. You see, here are the chunks of gravel in between there. Whatever that dark material is, that's your cementing material. Squeeze the water out, which I'm sure these pieces of gravel were deposited by water, and then overburden, 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 squeeze down, and then whatever was left in there, bound them together. It's the binding agent, okay? And that then finally becomes rock, sedimentary rock. It's gravel here, it's sand here, it's silt here, it's clay here, it's whatever it is, little pieces of rock. The pressure, the overburden, is your compaction process, and then the leftover material that's in between, that binds them together. That's the cementation process, and at some point there, you have another rock, made out of little pieces of other rocks. These are some white rocks, some pink rocks, and some black or darker rock. Well, all of them are in there making one piece of sedimentary rock now. Sandstone, siltstone, claystone, conglomerate, breccia, whatever. This, if these were big chunks of gravel, this would probably be conglomerate, because most of these are rounded. They are not angular. I can't get my cursor. There it is. That one has a little bit of an angle, but most of them are rounded. If these were pieces of gravel, that would be conglomerate, not breccia. If those are pieces of sand, that would be sandstone. If those are little silt particles, that would be siltstone or mudstone. Okay. That's your lithification process. We're through now with sedimentary rocks. Pictures in your book. And I don't know if I agree with this one or not. There's two more pieces of breccia, they say. This one here looks a bit too rounded to be breccia. I would be tempted to call that conglomerate, but I don't know. This one, they do look a little more angular, so that second one possibly is breccia, okay, because they are a little bit more angular in shape. Okay, another nice picture they have here is sedimentary rock. I'm guessing that's sandstone. See how horizontal and level the levels are, the sedimentary levels are. They were forced together by the overburden for those on top, and they formed these striated bands. Higher iron oxide content in the darker bands, lower, more probably quartzy type layers in between. Definitely different types. These here, wherever it was, that one. You could tell those are different types of rock that formed those gravel pieces, and yet you form them. And here's your cementing agent was a reddish color. Here it was more of a grayish or tannish color. Okay, so just lots of differences there. And that one last slide on this is page 448 or your page 1713. This is a picture you'll see very similar to the road cut you drive down any highway in Alabama. If it's cut through a mountain, this is what it looks like. That's limestone. You can see some of that was layered, but it wasn't layered because of water sediment. It came out of solution, probably at different times. Okay, but that's limestone. Sedimentary rock formed underwater, and sometimes you'll find actually pieces of biological material left in there. Okay, now here is a good blurb, well worth your look, on page 449 if you have a big book, 1714 if you have the smaller book. It's a blurb on asbestos. Now that's a really bad word, isn't it? You hear asbestos, you think harmful, dangerous, deadly, okay, causing all sorts of problems, okay? You read this and you find out in reality, most asbestos is basically harmless. But that is harmful is really harmful, okay? So people shy away from any asbestos because they can't tell the difference, okay? And they name some different mineral names here. If you wanted to do something on asbestos, that would be a good paper topic. The bad stuff, the good stuff, the in-between stuff, okay? All right. It's a bad word nowadays. All right, next page, 450 or 1715, a nice blurb on science and society. These are usually really beneficial to read, so I'll let you decide whether you want to or not. It has several questions to discuss or think about. If some of that you read there, using mineral resources, if some of this is something that is interesting to you, that can give you some paper topic ideas, if you haven't already decided. Now, why am I talking so much about paper topics? Let's see. In this class, obviously one of my best classes of all time, let's see, how many papers have been turned in? Oh, 0. Okay? Folks, don't forget about your papers. You get them in the month of June, you still get a bonus point. You wait till July, you just get your score. Okay? No bonus added. Okay?
Wait, what paper is this?
What's that?
What paper is this?
Oh, yeah. If you read the syllabus, if you read the other materials under content in Blackboard, there's a whole one there on research paper instructions. If you listen to that first day's class of YouTube videos, I talked all over about that. Okay? It's all over the place there. Yeah, there's a research paper due. Of course, it's supposed to be a term paper, so you could take all term if you wanted to. Please don't. Get it done earlier rather than later. You don't want to, during finals week, to have to be worrying about a research paper. Well, in fact, it's too late then. But even right before finals week, you don't want to be worrying about a research paper. Get working.
Oh, okay. Something about a point for.
What's that?
Like, you mentioned something about is, you don't have any papers yet, and.
Yeah, I don't have a single research paper turned in yet. So please get working on those. That's why I keep bringing them up, encouraging you to work on them. Okay. All right. All right. Now we're ready for metamorphic rock. Okay. Now, again, metamorphic basically means big change. Okay. Big change in the rocks. What a metamorphic rock was a previously existing rock, and it actually was rock, not pieces of rock like sedimentary rock, but pre-existing rock that has been changed, and if you go back to that altered materials slide, you'll see changed by heat, changed by pressure, or changed by hot solutions into a distinctly different rock. It was one type of rock, and just the process of heat, pressure, and or hot solutions changed it into a different rock. Now, usually that does mean changing crystal structure, and we'll see examples of that. Now, the causes are usually associated with geological events. For instance, the movement of the crust. That's going to be the next chapter. We'll talk about that. The movement of the crust, number one, if they're moving against each other, friction produces heat. But also, banging against each other creates a lot of pressure. And sometimes the places where they join or meet or collide, you'll have solutions coming out of that, as in lava or something like that. They're usually talking about water solutions, but there all sorts of things can be happening there. So yeah, quite often they could be caused by the movement of the crust. Okay? The heating and hot solution from magma intrusion. Okay, now what does that mean? Okay. Let's picture, and we'll see this in a later chapter too, you have layers, seams, joints. We'll see all this kind of stuff talked about in later chapters. Little places where there's weaknesses. Well, if somewhere down under there you have molten, hot magma, okay, and you have these weaknesses or cracks or things here, that magma is under a lot of pressure because all this overburden is pushing down on it. It's trying to find some place to go, okay? Here's a really dumb example, but if you ever played around with something like silly putty or something like that, and you squeeze it in the ball of your hand, but some of it comes squirting between your fingers. It's the more pressure you put on it with your fist, the more it's forcing it out any opening it can find. Well, that's what they're meaning here. Heating and hot solutions from magma intrusion. The pressure there, if that magma can find a gap, find a weakness, find a crack, find anywhere it can go, then it's going to be squeezed up there and maybe carry with it some hot solutions of waters and chemical and other things like this. So that could be a geological event that causes some of this heat, some of the pressure, and some of the hot solutions. Now the temperatures must be high enough to cause recrystallization, but not melting. So here you have a fine line that you're having to stay between. If it's hot enough that causes the crystal structure to change, usually under a lot of pressure too, that has changed the rock, a metamorphic rock. But if you get too hot, what happens? It melts. What kind of rock would that become? Rock formed from molten rock? That would make igneous rock. So as long as you don't melt it, but you're hot enough to recrystallize it, that's a metamorphic rock. But if you melt it and then it rehardens, no longer metamorphic, it's now igneous. Okay? So fine line between the two. Okay? Here is a great, I found it, I like this. Okay? Remember we talked about a clastic sedimentary rock made out of clay materials, possibly silts, that formed shale. We mentioned mudstone, we mentioned claystone, but they also threw in there shale. That's a sedimentary rock. Now, basically, one of the ways that shale differs from the other two is most of the time shale is in distinct layers, okay? Whereas the others may just be globs of it, okay? But shale is usually in layers. Now, add a lot of heat and a whole lot of pressure to shale, and you lose that, the cementation process, you alter that and you change the crystal structure, and that becomes a metamorphic rock called slate. Now, have y'all ever heard of slate? I almost feel like running down to our downstairs half bath and bringing you up a piece of slate. You want me to do that? Yay or nay? Okay.
Sure, you won.
Okay.
Sure, work.
Okay. I'm going to stop the recording right now. This is a piece of slate. Okay. Now here's a place where I think I knocked it off and it broke a corner of it. And you can see, if you look carefully, there are sort of layers in there. Okay. The edges is harder to tell. It's dusty too. You know what slate is used for? Our church has some slate on it. This came from New Orleans. They had a huge fire in New Orleans. This was, I don't know when. Let me see if they have. 1795. They had a disastrous fire in New Orleans. Okay? And one of the things that spread the fire was that people were using what they called cedar shakes and other things like that, basically wood product, for the roofs of most of the houses. And that's where the fire spread from roof to roof to roof and just burned down these huge areas of New Orleans. Okay? So what they did, this was mined in Pennsylvania. They brought it down the river and they started using, and I think started requiring this to be used on the roofs. Now look at that. This is a metamorphic rock that was shale, layers of mudstone and claystone. If you felt of this, you would feel no grittiness at all, but it would be sort of sharp in places. That's because it recrystallized into layers. It was already in a layer and recrystallized into a harder layer. That's slate roofs. Okay? Our church has, the old part of the church has a slate roof. Okay? Now, you add even more pressure, more heat, for a longer period of time, you can actually change this slate into schist. Now, I don't know what schist looks like for sure. Okay? I can't even say it very easily. Okay? But it becomes a harder material. I don't believe it breaks into planes like slate does, so therefore you wouldn't probably use schist on the roof because it sort of gets distorted in that more pressure. And then, I don't know if you remember, the nice rock we saw at the beginning of the class, that one that had all that curve in it and stuff like this, different layers, and it said it was one of the oldest rocks that they've ever discovered on the planet, something like 4.8 billion years old or something like that. That was schist that has undergone more pressure, more heat, and changed it into nice rock. Okay. But then you add even more heat and more pressure to it. You actually turn it into molten material, and when it hardens, it became granite. Okay? That's igneous rock because it actually melted it. As long as you add the heat and the pressure and it stays solid, you can send it through the metamorphosis process. But if it ever got hot enough to melt, and even for a short time, and then recrystallize, it becomes igneous rock again. All right, so that was a classic sedimentary rock, shale, mudstone or claystone, okay, but shale in layers. Let's go to one that was chemical sediment, limestone, okay? If you put limestone under a great amount of temperature and pressure, you actually change the crystal nature of that limestone and it becomes marble. Limestone, a lot of buildings have limestone on the exterior and they look nice and white and pretty for a few years, maybe a decade or two, and then they get the algae growth, they get ugliness. They have to come in and pressure wash and clean it up, and it looks pretty for a time. And actually, when they pressure wash, they're really knocking off the outer layer because limestone is just not that hard. But once it becomes marble, you keep that color, you keep that shape. We were over in Italy, we've been there a time or two, when my wife has been on professional meetings, or we've had nieces and nephews that we offered to give them trips, and all three of four wound up going at least part of the time to Italy. And you can see these columns still standing with marble, and you still see a lot of the original colors and everything else. It's just beautiful stuff. It will wear away, it will, but not nearly as fast as limestone will, because it's metamorphosized. The chemical bonds are much stronger, much harder. Okay. Now, marble can be brittle and can chip away that way. It's still made out of calcium carbonate, so if you get too much acid on it, like acid rain even, it will begin to pit a little bit, but not nearly as fast as limestone will. But you add more pressure, more heat, helt it up, you melted it, and it re-solidifies as calcite, which is can be igneous rock if it came from melted calcite, or if it came out of solution, that could be that's just a mineral, calcite mineral. Okay, let's go back to another classic sediment rock. This is sandstone. Sandstone made out of sand particles. Remember, you've had the compaction and cementation. That's what made it into a different rock, sandstone. Okay? But you add even more pressure at higher temperatures, you actually fuse some of those crystals together, changing the crystal structure with the heat and temperature, and now you make another mineral, a rock called quartzite, which again is much harder. Sandstone, sometimes you can rub your hand over it and break off sand particles. It's just, if a weak amount of cementation or the compaction wasn't as great, one of the pieces I had from Winston County, you could rub off pieces of it with your finger and thumb, you know. But if you added more, quartzite is hard, hard, hard. Well, add more heat and temperature to quartzite, which is metamorphic rock, and it melts it. It becomes, when it re-solidifies as quartz, that's igneous rock again, or igneous mineral. Okay? Now, you can also have, rather than shale, you can have a very fine-grained igneous rock. Let's say rhyolite, I think, was one. Fine-grained igneous rock. Add more heat and pressure to that, and you wind up with schist again. This came from sedimentary rock. This one came from igneous rock. So even igneous rock, you put under enough heat, enough temperature, enough pressure, you can change the crystal structure to schist. Add more, becomes nice rock. Okay. Now the piece that we saw almost certainly came from shale because it was banded. Igneous rock wouldn't be banded. There would be no reason for the bands there. This came from sedimentary rock. But you can have schist and later gneiss that came from igneous rock, fine-grained igneous rock. This would be very hard, probably very old because it takes a long time to do, but you keep adding heat and temperature. If it melts, it goes back to granite, which is igneous rock again. Now this would be way, way, way beneath the surface of the earth. So even though that started as a fine-grained igneous rock, which probably formed as extrusive igneous rock because it's very fine-grained, cooled real quickly at or near the surface, or above the surface even, this that's re-solidified after it melted, it's way deep in the earth. That's going to be large crystal size, coarse grain granite, not rhyolite or something like that. Okay. Does that kind of make sense? A lot of blah, 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 right?
Yes, makes sense.
All
And
right.
blah blah blah.
And blah, blah, blah. Okay, good. I want to make sure of the blah, blah, blah. What's that?
Yes, a little bit of both.
Okay. I have to mix a little in, you know. Now, before we leave the page that's talked about, at the top of that page is a people behind the science, Victor Moritz Goldschmidt. Okay? He was Swiss born, but did most of his work when living in Norway, so he became a Norwegian citizen. And he was called the founder of modern geochemistry. That's geology from a chemical viewpoint. Really a nice article to read. Remember, if you choose to write on him, this cannot be your source. You have to get your source outside the book. The book can give you great ideas for the source, for the paper, but it can't be your source for the paper. It can be your source for your ideas. And if you read much about this, you'll see other names mentioned, Josiah Gibbs, and you might want to write on him rather than Goldschmidt. You'll see William and Lawrence Bragg, Max von Laue, okay? You'll see a lot of different people and events listed here. You can get a lot of different ideas for paper topics just from that one article. But this article can't be your source. You have to have your source outside. It can be a source of ideas, but not the source of your paper. Okay, moving on. How do we, you remember when we had igneous rock, we classified it by mineral composition or by grain size, how it was formed, temperature, all that kind of stuff. With sedimentary rock, we classified that by either clastic or chemical, and then particle size. There are ways of classifying that. We haven't talked anything about how to classify metamorphic rock. Well, I can't get the page to turn. Okay? Now maybe it will. Yeah. Here's how we classify metamorphic rock. And this begins on page 451 and I think continues to the next page. Okay? How are we doing on time? Okay. Almost to run out. I was going to take you to 6:45, but that's right, we stop at... No! We've actually gone over, haven't we?
I thought it was 6:15, but
Kind of, yeah.
Oh my goodness, y'all just got so enthralled with my blah, blah, blah. I put you to... okay, we'll start next time on classification of igneous rock with foliation, okay? Or something around there. Classification of metamorphic rock. I need to find my eraser. The cleaning lady came today, first time since the social distancing and all this went into effect. She really needed to work. My wife decided, well, let's let her come back. She wore a mask. I wore a mask anytime we were within not even within 6 feet, within sight of each other, but I stayed up here and worked or went outside to eat lunch, and she worked in here. She left. I didn't even know it. But anyway, she was here, so I had to rearrange everything in here, hoping she was going to clean in here. She didn't even come in the room, so everything's not where I usually keep it. But you don't care about that, do you? All right, what we'll do next time, we'll pick up with classification of metamorphic rock. Then we'll talk about the rock cycle. That's the last. So we only have a few slides left. So what we'll do next time is finish chapter 17. We'll get started in 18, but we'll stop next time at 4:15, not 4:45, and we'll have 2 hours of lab. Now that lab, let me get an idea from you. I assume since you're here, you can you have to be able to get on the internet, right? You're here. That's how you're doing classes this summer. So if we have a lab that is predominantly internet based, you can get to the websites that you need, can't you?
Yes, sir.
Okay.
yes.
So let's plan, I'll get the lab done. I'll post it probably sometime Sunday night. Well, no, probably, yeah, sometime Sunday afternoon or sometime Sunday. I'll try to put the lab out there. So if you want to print it off, you can, or you can do it just from your, I don't care how you do it, but what you'll need to do is go to a website. I'll tell you what website to go to, and we'll talk about how to do it. And I'll give you 2 hours of talking about it and dealing with it. And if you want to do the whole thing during those 2 hours, I'll stay on board for it. If you want to get off and do it at your own pace, you can certainly do that as well. But I'll give you a full 2 hours to discuss the lab and ask questions and see if you can get everything to work. So that'll be the last 2 hours from on Monday. So we'll start and finish chapter 17, start chapter 18, and then stop at 4:15 and have at least 2 hours worth of lab if you want to take it and do the lab for 18. And then after that's over, I'll post the test for chapter 17. Sound good?
Sounds good.
All right. Have a good weekend, a safe weekend, and we'll see you on Monday. Okay?
Thank you.
I'll stop the sharing, and unless there are last questions, I'll end the meeting. Any last questions? All right. Take care. Oh.